Hello, I will be giving a final overview of my Semester 1 Advanced Technologies project, an asset validator created with Unity UI Toolkit. This is the asset validator window that is opened up on asset import or by clicking on Tools, Asset Validator, Asset Validator. This is an asset validator setting. This is what a designer would use to change different parts of the validation process. Each setting gives a tooltip to ensure that the designer knows what they are changing. In the actual asset validator window, you can toggle whether something will be validated upon the validate button. Upon hitting validate, I get a passed result as the file size was less than 10 gigabytes and the prefix of that name was T underscore. The artifact is comprised of five main primary scripts, each handling different parts of asset validation. Asset post-process script opens up the asset validator window upon asset importing. The imported asset will be selected and then the asset validator window will be opened. This was the result of a feature request I received in one of my presentation sessions where this was a requested feature. The asset validator namespace script holds all the constants used throughout the different scripts. Throughout this project, all of my scripts are heavily commented. That way, to make it easier for someone to expand the project in the future, they understand how different parts of the code works. The primary part of the asset validator namespace script is the settings base class. This is what every setting inherits from, so that way they all receive log leveling and tracking of their own results and UI visuals that are associated with this setting. For example, general file size settings inherits from the settings space. This use of object-oriented programming is used throughout, and this polymorphism is very, very useful later on in the scripts. For a designer to expand this in the future, they would simply need to just create a brand new settings that inherits from settings space. Inside of the namespace constants contains all the constants used throughout the scripts. This is because it's preferred to define strings and then reference their variable. That way, manual string lookups aren't used. Importantly, we have a list of the settings that are references to UI Toolkit's settings inside of here. This is to link the UXML to different scripts. The reason why we do this is to make it as simple for a designer as possible to expand this in the future, as that was a main goal throughout this artifact. Next, we have the scriptable object asset validation settings. This was designed to be as simple for a designer as possible to see in the inspector. As such, tooltips are added throughout to make things as clear as possible. For a designer expanding in the future to add more validation checks, they simply add their created settings as a public variable in the scriptable object and add this to the settings list. This is because this settings list is looped through and then linked to the UXML later. Validate object is the script that contains all the validation checks that are done on different objects. Everything is declared as static to make things as optimized as possible, as this is done on compile time as opposed to runtime. For a designer, it's very simple to add on additional checks in here for their brand new setting. Finally, we have Asset Validator, which is the actual editor window that we see. Upon the window being opened, we link the UXML and the events. The XML is linked using the constants that we declared in the Asset Validator namespace. Upon clicking the Validate button, we will check which toggles have been enabled and then validate the object depending on their type. Once we have validated everything, we then take the results and update the UI visual elements based on whether they passed their asset validation check or if they failed. For adding new checks, it is simple for a designer. They can simply copy and paste one of these toggles that has already been set, declare them in the asset validator namespace. For presentation 1, my stage was having an early version of the tool window that displays the selected asset's name in a UI label, and the first asset validation check of is power of 2 for checking the width and height of an image to see if both are powers of 2. The feedback I received was having an image of the asset that was selected, developer settings for asset settings, and selecting multiple assets/assets inside of a folder. By presentation 2, I implemented the image of the asset selected and added placeholder text when nothing is selected, along with the asset validator opening on import of a valid asset type and selects them automatically when they have been imported. The feedback I received was to continue improving the UI, such as having drop down to validation methods and having more validation methods. By presentation 3, I added a drag and drop scriptable object, which is the asset validator settings in response to presentation 1's feedback, along with the scriptable object being split into 4 sections, such as general settings for all valid asset types and validation for texture 2D, audio clip, and mesh asset types. The feedback I received from this was add even more validation methods and greater developer control for the scriptable objects, such as logging colors. This was then executed in the final artifact. Hello, I will be giving a final overview of my Semester 2 Advanced Technologies project, a shared machine learning brain between a hummingbird and kart racer. My artifact consists of 2 major parts, my kart agent and my hummingbird agent. Both agents have been trained individually in their environments to ensure their systems work correctly. Starting off with my hummingbird agent, this is a trained brain of my hummingbird agent that's been trained specifically on hummingbird agent environment. This environment is a floating island consisting of rewards in the form of nectar that they achieve by putting their collider inside of a flower bud. The agent on screen currently is an agent that's been trained for above 2 hours in this environment. This agent has radar sensors that detect where obstacles are and where the colliders of the next flower it wants to go to are. This agent is rewarded for more nectar being achieved per run, the nectar being the reward. This agent has 5 actions that it can take, going up, down, left and right, and changing its yaw and pitch. The kart agent environment is deliberately similar to the hummingbird agent environment. This was to make it easier when translating logic between the two of them. This also extends into the script structures of both agents. The kart agent similarly has radar sensors to detect where obstacles are, that being the walls of a racetrack. They also detect where the next checkpoint collider is, which is how they reward themselves. Unlike the hummingbird agents, the kart agents only have 2 actions, that being forward and backwards and left and right. It was noted in the presentation that the kart agent might be trying to enter into the center of a checkpoint collider, but as they don't have a way of moving up and down, they are unable to achieve their location. This did not affect the learning of the agent, however. Both environments use 3 major scripts, that being the reward, the environment, and the agent themselves, with the reward of the hummingbird being related to flower.cs and the reward for the kart agent being track.cs. Flower area and racetrack.cs are the environments of the 2 machine learning agents, and hummingbird agent.cs and kart agent.cs being their brains. Both reward scripts are very similar to one another, that being ways of rewarding, resetting when we reset our agent simulation, and data associated to the rewards. The environment scripts handle the interface between the agents and the rewards. They keep track of how big their environments are through how many rewards are in them, along with other parameters. These interfaces then communicate with the agents. That way they can reward themselves based on information provided through flower area and racetrack. Again, these scripts were deliberately made to be similar to make bridging the logic of a shared brain as easy as possible. Finally, the agent scripts themselves. The initial implementations of both were focused on ensuring that they could learn from their own environments. As such, part of their implementations are very much exclusive to their own environments. For example, the Hummingbird agent has additional action buffers that the kart agent does not have. This was to make the training of the Hummingbird agent be more effective. This is where it was noted that observations, action buffers, and sensors must be identical in agents in order for their agent brains to work. It was established that 10 observations would be made for both agents, and a number of action buffers would be free. This required the Hummingbird agent to have less actions, as it initially had 5, alongside a car agent needing an additional action. However, with the car agent, this could be buffered with a null reference. As for sensors, it's more important that the car agent has sensors behind it to detect checkpoints that it's already completed. As such, additional sensors were added to the Hummingbird agent to bridge that logic. The stage of the project on presentation 1 was that research was conducted on how to implement machine learning. It was set out to avoid the use of visual learning as it was too complex for the timescale of the artifact, and kart racing and Hummingbird demo games were chosen for the training. The feedback received from this presentation was to begin the development of the agent games and training. Presentation 2 stage was having the Hummingbird agent game created and Hummingbird agents were trained. The karting minigame was imported and features that needed to be mapped to both games were identified. Those being raycar sensors, so the number of sensors and number of raycars in each sensor, and a number of observations. Also, the number of action buffers/actions that the agent can perform. The feedback received in presentation 2 was to begin to work on a second game, the karting game. Finally, for presentation 3, the original kart game was scrapped as it was not compatible with the Hummingbird agent. Instead, a bespoke game was created. Karting agents were trained, and the initial implementation had them learn backwards as reward structures needed more development. They were not punished for driving into walls, and checkpoints can be completed in any order. The second implementation had them learn effectively, as they had to complete the track in order, were punished if hitting walls, and their rewards would multiply with each successful checkpoint reached. Finally, the Hummingbird agent brain was tested on a karting agent, and this identified that more work and bridging their logic would be required. The feedback received in this presentation was to check the observation being made between the karting agent and their next checkpoint, as they might be trying to get to the center of a collider that is above their position, and to try and put the kart agent brain in the Hummingbird agent to see what would happen. These were addressed in the final artifact.